Last time we talked about subatomic particles like electrons, neutrons, protons, photons, etc. Very small particles that don't move the same way that a baseball would. Okay, and this is why it falls into the field of quantum mechanics. In particular, we talked about electrons, and we said that electrons can have certain energy levels, right? They can, depending on how fast they move, and then they can move between energy levels if they're excited, if energy is put into it, like if you burn them, or if even light just shines on them. Some of the electrons can go to higher energy, and then they also come back down. And when they come back down, they release energy in the form of an electromagnetic spectrum. And that goes all the way from radio waves to gamma waves, and through the middle between 400 and 750 nanometers, which is the visible light, so that we can actually see. So when we look at an object and it's in the red color, it's actually around 650 nanometers. We can see that it's electromagnetic radiation. It's not harmful. But and then we looked closer into the Bohr model of, in particular, of hydrogen, which is shown here. Okay, this is a hydrogen, and it shows the different quantum levels or energy levels here. Energy level 1, 2, 3, 4, and so the further they get away from the nucleus, the higher they are in energy, right? So the further away you are from the nucleus, the faster you have to move, and so then therefore you have higher energy. And what is shown here are 3 of the transitions that are observed for hydrogen. In particular, I'm going to single out the one that produces a line at 657 nanometers. It is for the electron that comes back down from the 3rd quantum level to the 2nd. Okay, so if you fill an electrode with hydrogen and you apply current to it, it glows in a purplish, whitish purplish color, and then you can split that light through a prism, and you get 4 different bands. And so one of them happens to be the red light from the 3rd energy to the 2nd energy level. Okay, and so you can actually use an equation to calculate that wavelength that's particular for the hydrogen atom, right? So this is called the Rydberg equation. It's shown here, all right? So 1 over lambda, which is the wavelength in meters, equals a constant. This constant here is the Rydberg constant. This is the Rydberg equation. So this constant is actually unique for the hydrogen electrode, right? Not electrode, atom, for the hydrogen atom. It's about the electrons that are moving. And so here what we have is we have n, which is the quantum level, either 3, 4, 5, 6, the quantum level that the electron originated from, and then of course we filled n in here. This is the final level 2, because all of the visible transitions are on the 2nd quantum level. So this is 2 squared. So 1 over lambda equals that Rydberg constant times this ratio here, 1 over n for the final quantum level times 1 over n of the initial, right? So if we calculate the lambda for that red band, that's going from the 3rd to the 2nd, n is going to be equal to 3. So then this turns into 1, so 2 squared is 4, 1/4 over 1 over 3 squared, which is 9. And so that ratio equals 0.1389. And so if you then do 1 over lambda equals 1.097 times 10 to the 7 per meters times that 0.1389, you get 0.15237 yada yada times 10 to the 7 per meter. Of course, you then have to multiply by lambda and divide by that, and you end up with exactly that, 6 0.56 times 10 to the minus 7 meters, which is equal to 656 nanometers, which is equal to, well, basically 657 nanometers to the red band. So you can use that for, you can put 4 and 5 in there, and you should be able to calculate the other bands, and 6 as well for the fourth band. So that's for the wavelength. Now, as far as the energy is concerned, you can calculate the energy of an electron on a quantum level by simply taking RH, which is another Rydberg constant, depending on which element we're talking about, divided by the quantum level squared. Okay, and there's a negative here, and then you can, and if you want to figure out what the change in energy is, you have to take delta E. Okay, and so you can actually take delta E. The change in energy is going to be, you can take minus RH. If you set them close together, you take that out of the equation, so you have minus RH times, of course, 1 over n final level of squared minus 1 over n initial level squared. So let's use that equation. I'll give you what RH is for this particular problem here. Consider the transition of an electron in a hydrogen atom that moves from the third energy level to the first. So we're going from a higher to a lower level. That means we're going to release energy. So that should have a negative value. Okay. All right. So the change in energy is going to be equal to that constant, 2.18 times 10 to the minus 18 joules, times 1 over 1 squared, right? That's the final level, minus 1 over 3 squared. That's the initial level. So this ratio here is, of course, boils down to 1 minus 1/9, which is equal to 0.888. And if you multiply the two, you get, I'm sorry, this is negative, of course. The equation is negative RH, right? Okay. So it's right here, negative RH. I forgot that. So that's important because we're releasing energy, right? So it's minus 1.94 times 10 to the negative 18 joules is the energy given off, which of course you can also calculate with this equation here. Energy equals Planck's constant times frequency, and you can get the frequency from well, you'd have to calculate the wavelength then, so we'd have to use a different equation. So this one is easier in this case. All right, so let's do another one. Calculate the energy in joules required to excite a hydrogen atom by causing an electronic transitions from the first to the fourth. So now we're putting energy in, so the change in energy should be a positive value, right? Because we're going from n equal to 1 to n equal to 4. So we have to, in order to get that electron to go up there, we're going to have to stick energy in there. So delta H is going to be equal to negative RH, which doesn't change. It's still minus 2.18 times 10 to the negative 18 joules. And so then our ratio is 1 over 4 squared minus 1 over 1 squared. So that's 1/16 minus 1. That ratio is 0.9. It's going to be negative because you're subtracting a fraction minus, so it's negative 0.9375. And so if you have minus negative 2.18 times minus 0.937, you get a positive number, so the change in energy is going to be equal to 2.04 times 10 to the negative 18 joules. All right, let's take a look at photons. Photons are light particles. Mentioned it already, but this is the first slide that addresses that. So Einstein actually came up with this postulate that light is not only a wave, but it's a particle. And if it's a particle, it has momentum, it moves, it has mass, and then and so those are called photons, light particles, and that's what's emitted when the electron comes down from a higher to a lower. It's a photon, and it travels at the speed of light, and once again it has a wavelength and a frequency. But if it has also mass, then we should be able to use that in an equation. So de Broglie postulated or came up with this particular equation. That's the de Broglie equation, where the wavelength is equal to Planck's constant divided by the mass times its velocity. So we don't have to have which quantum level it goes from where. We just need to know its mass. If we know the mass of the photon, and we know its velocity, then we can also calculate the wavelength, which can be quite useful. So Planck's constant, I want to remind you, is 6.63 times 10 to the minus 34 joules times seconds. Those are its units, okay? But if we're going to use that in this equation, and the mass is going to be here in kilograms, and the velocity is going to be in meters per second, then the units don't cancel, because we need our units to be in meters, of course, to have a legitimate wavelength. Which, if you remember, joules is actually a derived unit. Okay, it's not an SI unit. So if we replace joules with the SI units, which is the SI units for joules is kilograms times meters squared per second squared. So you've got a force that's acting on an area. Okay, if you plug that in for joules here, replace that, so you have seconds per second squared times seconds, so one of those goes away. So the new units here for Planck's constant are going to be kilograms times meters squared per second. Now, there's still, the 2 went away to a 1, right? So one of the seconds cancels, the other one does not. So now when you plug that in, right, you've got kilograms times meters squared per second squared. Now all of a sudden you're dividing by kilograms times meters per second. Per second cancels, kilograms cancels, one of the meters cancels, and our units are in meters. It's important to pay attention to the units. Alright, so if we are going to calculate the wavelength of a subatomic particle, right, golf ball, not subatomic, way too large, but we can do this calculation just for the sake of doing a calculation. So let's calculate the wavelength of a golf ball using the de Broglie equation. And this golf ball has a mass of 65 grams and travels at a speed of 240 meters per second. So lambda is going to be equal to Planck's constant, 6.63 times 10 to the minus 34 kilograms meters squared per seconds is what we said. And then the 65, it has to be in kilograms. So there's 1,000 grams in a kilogram, or 10 to the negative 3 grams in a kilogram. 1 kilogram equals 10 to the third. So it's times 10 to the third kilograms, and so the velocity is 240 meters per second, or if I write it like this, per second, then you can see that this cancels nicely, right? And so it's important. See, here your units are important, because if you plug in 65, you're going to get the problem wrong. You have to put 65 times 10 to the 3, or you know, anyway. So then when you plug that in, you get 4.25 times 10 to the negative 35 meters. It's going to be a pretty small wavelength. All right. Let's do one more. calculate the wavelength of an electron. Now we're talking that we can that's actually a real problem that has a mass of 9.11 times 10 to the negative 31 kilograms, which happens to be the mass of an electron, and a velocity of 4.7 times 10 to the 6 meters per second. So now we have an electron that's traveling, and electrons are going to travel in waves. Okay, same equation. Lambda equals Planck's constant, 6.63 times 10 to the minus 34, using the new units, kilograms times meters squared per second, divided by, the mass is already in kilograms, so that's good, 9.11 times 10 to the negative 31 kilograms times its velocity in meters per second, 4.7 times 10 to the 6 meters per second. Plug it into the calculator. Kilograms cancels, per seconds cancels, one of the meters cancels. Our units are going to be in meters. I get 1.55 times 10 to the negative 10 meters. So that's outside of the visible range. Okay, moving along, now we're going to look at the Schrödinger equation and Heisenberg's uncertainty principle, right? So as we said, electrons don't move in a precise path. In fact, electrons don't even really move in waves because they are also attracted by well, they move in waves, but there's also that nucleus, right? So you've got a positive charge in the center that's going to keep it in a certain path, right? So it's more likely that an electron moves in some sort of orbital here, right? And so now we're getting closer to where we want to get. We want to know what path these electrons are on, right? And so there are two components to a particle that's in motion, right? So you've got a position, it's somewhere, right? So that's X is the position here. This is the Heisenberg's uncertainty principle, which says that well, we can neither know the position nor the velocity together. We can just do one, right? Okay, hang on. So X is the position. So this is the change in position and the change in velocity, right? And so let's say if I know the position, right? Let's say I found it, the electron is here. That's just great. But then I don't know where it's going, right? Is it going to go here? Is it going to go here, there, or there, right? So it's hard to predict. Or I can determine its velocity, and then I don't know where it is. So you can only have one or the other. This here is the mass in kilograms, and so that's known as Heisenberg's uncertainty principle. All right, so what's the useful thing that we can get out of this here, right? We ideally would like to know what the electron is doing, where it is moving, so we can determine its properties, right? And so for that, that's called a wave function. So we use this phi there, right? And it's more useful to determine the probability of that particular electron. Okay, where's my probability of finding it, right? So if I have a nucleus again and the electron is here, it's not going to be there permanently. It's going to move, and sometimes it moves in very interesting path, right? It'll fill out this dumbbell, right? It really depends on where the electron is. It'll just move like this, or it's going to be in a sphere. It's going to move around like that. Sometimes it makes even more interesting shapes, as you will see. So it doesn't do us any good to find, okay, here's the electron. It could be part of one of those path, or there's actually things that look like that. there are two components like this, and some things that look like butterflies, and so we'll actually look at that into more detail in a minute. But again, it doesn't do us any good to find out where it is, but it would be good to know where its probability is, so then I can look at this entire regions, and those are regions of electron density, and then it's electron density that overlaps or gets transferred where bonding takes place, and that's what this chapter is pretty much about, right? So looking at this is for a hydrogen atom, right? We're still looking at hydrogen, and there's a single electron there. We ought to be able to find out where that is. And so there's the further away you get from the nucleus here, like if you get 100 picometers away, you have very little chance of finding it. That it's more probable to find it somewhere here, right? So it's more likely to be somewhere here. But even that doesn't do us any good. The really useful one is the probability function, as I said. And so now we know we can look at the distribution function, right? It's never going to be right at the nucleus, and it's not going to be this far out, right? It can be here, but there's this maximum here, right? And that maximum is actually at 0.59 angstroms. Remember, that's the unit of distance that we use for distance, right? Angstroms for atomic distances. And so this happens to be the Bohr radius for hydrogen, right? Niels Bohr. So, and that's the end of lecture 2. And we'll have a final lecture on quantum numbers, which will describe where exactly these electrons are. So I'll see you in a bit.